Thank you very much. So, my talk today is on modern plan checks and how to avoid being in the New York Times. Let's get started. As she said, I am the founder of Mobius Medical Systems. It's a company I own. I leaded the development of all of the products that we have, and so I am both personally and financially attached to them. So I will be talking about Mobius 3D in this talk because it does have a lot of implications for plan checks. And that's me in a normal work day sitting on my pile of money since I have a company. It works just like that. So, modern radiation treatment plans are very complicated, but one of the things I noticed is over these last 20 years, the QA tools haven't really kept pace with the planning systems. There is a lot of scrutiny in radiation oncology QA, partly due to the series of articles in the New York Times that everyone's heard about over and over now. And one of the things I think is a really good way to combat this is for everyone in the department to have a good understanding of the entire radiation treatment process, from commissioning to delivery, to help ensure safe treatments. So a little bit about me, a little bit more about me. I didn't realize the intro would be so long. I was a PhD student at MD Anderson Cancer Center. I developed open source dose lab software there, so I've been involved with software quite a bit. I worked at the Methodist Hospital for about 6 years as a clinical physicist, and then I left to found my own company, Mobius Medical Systems, to develop Dose Lab Pro, Mobius 3D. Early this year, we released Mobius 3D. It's in use in several dozen clinics right now, and a lot of what I'm talking about and how to fix plan check errors and common errors are actually coming from some of our early sites, little tidbits of information we found. So let's talk about error rates in general. Let's say your clinic treats about 40 patients a day, either one heavily loaded machine or a couple lighter loaded machines. You're going to treat about 10,000 fractions per year. If you do that with a 99.99% success rate, that means every year you're going to mistreat one patient. And 99.99% is really high, and it sounds nice, but we also have to make sure that every system, the Linac and planning system, has been commissioned. The planning was done correctly, patient setup and positioning was done correctly, and the delivery was done correctly. All of these have to be working together to not mistreat a patient. So, I said this talks about how to avoid being in the New York Times. Let's look at what the New York Times actually identified, the errors they identified in radiation treatment. And if you look down through this list, there's nothing that really jumps out as being just terribly wrong that you couldn't imagine a standard clinic doing. There is a simple Linac calibration error. Also, because Linacs have to be calibrated site by site, you enter that same number in your planning system. That number did not match. Wrong detector used to measure small field alpha factors. TPS calculation errors. Wrong patient treated. Wrong patient positioning. MLC leaves failed to move during delivery. This is one of those things that it sounds really bad because we expect the MLC leaves to move for IMRT treatments. One patient, they did not. It was not caught for a few fractions. And it's one of those errors that looking back, you say, well, how did my therapist not notice that the MLC leaves weren't moving? Well, they're not the ones that made the plan. So a lot of these errors, you look back on and you say, well, it's not, you just can't imagine your clinic being completely immune from any of these. Missing physical wedge during delivery. Jaws open too wide for an SRS cone. This is something the machine did not talk to the SRS cone when it's inserted, so it did not know the maximum field size and was input wrong. One, in general, QA not sophisticated enough for IMRT, and the clinic moved to IMRT. And then there is a brachytherapy prostate seed error. So, takeaway message from this is that errors can be hard to see. And all I do is browse Reddit all day long, so this is just going to be littered with pictures from the internet. So get used to it. So what was a plan check that talks about modern plan checks? Well, back in the good old days, I'm a little young, so I have to rely on other people's experience. Plans consisted of open fields with a single block. If you wanted to get fancy, you threw in some physical wedges. What this led to was a large volume of uniform dose. And this is extremely important because we've moved away from it now. That means if you did not set up your patient correctly, you missed it by a few millimeters, one direction or another, that wasn't that big of a deal. If you did not commission your planning system perfectly, it wasn't that big of a deal. A 1% error in commissioning your planning system led to a 1% error in your patient dose. It's pretty much that simple. And if you wanted to check a patient plan, you did a secondary MU check with a very simple calculation, and you had another pair of eyes look over it and make sure that the wedges were put on in the correct direction and life looked good. Well, that's not the case anymore. That's not how we plan patients for the most part. The planning systems are significantly more complex, as everyone knows. They offer enormous amounts of choices per plan, per treatment. We also conform the dose to targets. So we have high dose gradients everywhere in the plan. If you miss your patient positioning just a little bit, you can completely miss the tumor now and shift that dose into a critical structure that's nearby. Not only can you conform the dose to a target, but you also get to choose where the dose that doesn't hit the target goes. Do you want it to go on top of the target, to the side? What critical structure do you want to put more of that dose onto? So our IMRT systems get to move that dose around from target to target. And we accomplish all this with modulation. The MLC leaves moving over and over and over again. One of the main points of this talk is going to be the more modulated your plan is, the more you've magnified all of your calculation errors and all of your patient setup errors and all of your delivery errors. So it's not something that's bad, that's how we get good conformal plans, but you have to keep in mind that you've magnified every error in your system for each additional MU you use to treat a patient each time you move your MLCs. So plan checks have to account for all these new complexities. And one of the big things we've added recently is patient-specific QA, because we kind of understood that our old way of checking plans wasn't going to quite get us there for IMRT. So this is kind of how I view, we get these new fancy treatment plans, but we haven't really redesigned our QA system. We just keep adapting it one after another and keep adding things to the check process, hoping that the final answer is going to be correct. So graphically, here's a good left to right, old 3D CRT, and then we got IMRT, and now we have VMAT. And this is a very beautiful picture, and it shows the picture on the right is a lot prettier than the picture on the left. What it never shows, and what your planning system doesn't show, is that the picture on the right is also a lot harder to deliver. After 10, 20 fractions, it's hard to set up the patient with that level of accuracy. It's hard to make sure your machine has delivered everything correctly. It's hard to make sure your calculation was correct than it is the picture on the left. So while one's prettier, we also have to keep in mind we need all parts of our system to be running better. Why aren't there better QA tools? My company makes QA equipment, and one of the first things I recognize is that when I use Pinnacle in my clinic, there's one planning system to QA. Now that I'm a QA vendor and we see the complexity that exists everywhere, it's a lot harder. There are different Linac coordinate systems. When your gantry is pointing down, that can mean 0 degrees, it can mean 180 degrees. I'm fairly amazed that this is allowed to change. Same with the centigrade per MU. That is just completely determined by how your physicists would like to set up their centigrade per MU for that linear accelerator. That's how we can get 30 or 40% calibration errors, because they're allowed to vary that much. MLC transmissions and capabilities vary greatly. There are tons of types of deliveries: static, moving gantry, MLC, small, large MLC segments, et cetera, et cetera. Third party and even some OEM accessories like the SRS cone do not always register being inserted into the beam, so we can't always do an automatic check to make sure things are working correctly. Physical wedges, there's aftermarket physical wedges, dynamic wedges, virtual wedges, motorized wedges. There's so much complexity that we have to design for. And if you come tell me I did a calculation with the 6MV beam, now I have to ask, was that 6MV traditional? Was that SRS mode, which has a smaller flattening filter? Or is that flattening filter free, which we've taken the flattening filter out? And all three of those have completely different dosimetric capabilities. So you can't hand me a plan that says 6MV, 200 MU, and expect me to have any idea how to calculate that, because I don't know what 6MV that is. I don't know what centigrade per MU factor your clinic uses. It's a very interesting problem. And of course, we can deliver with a customizable dose rate, which means the MLC speeds can vary. So Basically, not everything is intuitively designed. It's not something you just walk up to, use immediately, and have a great understanding that what you did was completely correct. Let's talk about beam measurements, the start of any planning system. So I'm a physicist, and we spend a lot of time measuring dose profiles and output factors and water tanks during commissioning. We then input all that data to our planning system, and a beam model, like Nico's talked about, is created to calculate the 3D radiation dose. Data is often directly copied to the MU check program due to ease of setup. And the rest of this talk is going to be about all the steps along the process and where to look for errors and how errors can accidentally get propagated. So we're going to really hit on a lot of these things. So the first thing I did is I measured one set of data. I copied that to my MU check system, which I expect to check my planning system. Why did I do a full set of measurements in the first place? Upon commissioning, we always do a full set of measurements. There are, indeed, Linac to Linac performance variations, maybe on the order of 1% or 2%. And physicists internally debate whether we should do a full set of measurements every time we get to Linac or if we should use reference data. The reference data is not going to match exactly our particular Linac. But on the other hand, if our particular Linac changes over time, we're not going to recommission the planning system either. We're just going to try to put it back where it was. I personally really like reference data because it removes a large source of, a large error source out of the equation. That doesn't mean that you don't measure your machine as if you did not have reference data, but use reference data and compare everything to it. This is my particular choice. Now, we don't always have that option. So what are measurement problems that we see? Water tank scan settings are mislabeled. The water tank setup was incorrect. We didn't use the right detector to measure the right things. Being a physicist is difficult. We're just a great group of people to do the job we do, and one of the things we have to do is understand that for each type of measurement, for each type of measurement, we have to use a different type of detector. Small fields, we're going to have to use things like diodes. Why don't we use diodes for large fields? Well, we can't because they have a lot of energy response, and large fields have a lot more low energy scatter plus high energy, so you can't use a diode. You have to switch the detector. So I talked to some people at the RPC. I said, what sort of measurement problems have you guys discovered? One clinic had wedge factors incorrectly entered in their planning system by 10%. RPC measured that. They found there's a 10% error. They looked back at the annual QA. The physicist has caught that every single year. He caught that it was 10% off, but nothing was corrected. Another clinic, their electron output factors were measured with the wrong SSD. They lowered the water tank to be able to set it in the beam. They forgot to raise it at the end. They did not, on their annuals, recommission the full set of output factors, so they didn't find that. Calibration error. Sea level atmospheric pressure was used for an ion chamber rather than, I believe they were fairly high up, 10,000 feet, resulting in a 25% error. So how do we check these measurements? We can't rely on the planning system or MU verification software to check these measurements for us. The Varian Golden Beam data is a great set of data. I recommend using it or manually comparing if you can't use it directly. If you have a different type of machine, there are tons of journal articles that will give you consensus data for output factors, PDDs, etc., especially if you're using an SRS machine with cones. Even if you measure incorrectly with the wrong detector, as long as you check your answers at the end, go back and look and see what do other people's output factors look like, and then notice, well, mine are 30% different. That can solve a lot of problems. So, and ensure annual QA is being performed, and if you find a mistake, look into it and fix it. It only takes one little thing along this process for everything to just go haywire. So we've measured our beam, now we've pulled in our planning system, and we get to do some beam modeling. For those of you that have not seen beam modeling, I would like to say that it is much more complex than even all the options you have when you create the treatment plan in the first place, depending on the system. Furthermore, because we have a lot of flexibility in making a beam model, we can create a beam model that works pretty well with the water tank measurements we just took, but it doesn't work that well on patient measurements. There are a lot of reasons, but that's we don't have time to get into that right now. Here's a good example of measured in blue, computed in green. These reports are available in all the planning systems. I highly recommend everyone is familiar with how well their calculation matches their measurement, because you're not going to get any better than this accuracy, than the accuracy you see in a water tank. That doesn't mean it has to be perfect everywhere, but you should have an understanding of this is as good as my calculation is ever going to be. So, Nico's talked about this a little bit. Let's get into a accuracy example. Say we modeled it, there's some 2% differences in the water phantom measurements. Well, now we're treating with IMRT or VMAT, so there's maybe a 1% difference because our MLC output factor is not measured, not modeled properly. And we're also off center, so that adds another percent. The PDD is not perfect anymore either, that's maybe another percent. There's some heterogeneity effects because we're not using Monte Carlo. And then we also chose the medium quality dose calculation option. That's just most of the way there, but we get another percent error. So all these can be 0%. They can all add up in the same direction or nothing. So at the end of the day, just from our calculation system, depending on how accurately we modeled things, we get 0% error or 8% error in this case. So very specific tips for modeling an eclipse. I know this is not something that most dosimetrists end up doing, but everyone can look back at their beam model and see if these are correct. Eclipse actually is a fairly easy system to model in. Varian does a lot of things behind the scenes that does a good job automatically. But there are 3 numbers in Eclipse that you really have to pay attention to because they can enormously change your results. Dynamic leaf gap, the source size, the MLC transmission value. Those numbers should be, one, you can physically measure them, but every once in a while, for things like the HD120 MLC, you'll physically measure a leaf gap of, say, 0.3 millimeters, which is probably the correct measured answer. But the system's model actually works better with a value of around 0.8 millimeters. And the difference between that can be 3 or 4%. So we don't even have to just measure these correctly. We have to make sure that our final dose calculations are correct. So one way of doing that is comparing these values, looking at publications, comparing them to consensus data. And even if these are measured and input correctly, that's not a guarantee that your final dosimetry is perfect. You actually do have to look at the final results in addition to your pure beam model. Pinnacle is a lot more fun because the Pinnacle beam model gives physicists just complete control over every factor they have. It's a really great research tool. It's an interesting clinical tool. Look in your Pinnacle beam model, the first tip I have is ask your physicist, ask who modeled it, are there multiple beam models? If so, that needs to be fixed. You can create a model for a 2x2, 5x5, 10x10, 20x20 field, and each of those will match what you measured in your water tank just amazingly well. But now you tell Pinnacle to calculate a 4x30 field with MLC leaves, and all of its modeling parameters are completely different because you did not use one model to try to fit all of your data. Make sure there are MLC-defined profiles in there. We're treating with MLCs. We're overlapping MLC segments. We have to make sure the MLC profiles are modeled well. And since most parts of the model are adjustable without boundaries, we need to look at consensus data again and make sure that we're getting about the same numbers other people have. The JACMP has a few publications on what values they have. Pinnacle comes with some sample beam models, which are pretty reasonable. So we can just make sure that we didn't accidentally input one number that's actually affecting our dose calculations in patient, but it's not noticeable in water. If you have XTO, I recommend you should talk to someone that uses XTO, because I'm sure there are some good modeling tips with that. I don't know any of them, though. So, how do we check our beam models? Of course, we can go back and look at the planning system software and see, did the 2 lines match up? I mean, that's always a good first step. But there are more things we can do. $1,200, you can have the RPC mail you a phantom. If you're in clinical trials, you probably have already done this. You can do it again. You can do it for your other machines. It's fairly cheap. $1,200 to make sure that you can plan something, deliver dose to it, and have all that come out accurately. They'll give you OSLD measurements, they'll give you film measurements, compare it to your planning system. You can do calculations using reference data. That's one of the things we built into Mobius 3D. We don't want people to import what they measured. We want to use a consensus set of data and then let people make minor adjustments, but we want to plan for errors in beam modeling or errors in measurement. Of course, the big one is performing measurements of IMRT and VMAT plans. Again, do not ignore failures. This is going to be another common theme. It's far too common in this field for us to ignore failures in MU checks, failures in IMRT QA. Those failures could be telling us something, or those failures could be that our QA system's not good enough, but we can't just ignore them. Check MLC defined output factors. This is actually one of the big things, is we don't actually check MLC output factors when we commission a beam model. This is a very simple test. The RPC comes and does this when they do site visits. They set your jaws to 10 by 10, they set your MLC to 6 by 6, 4 by 4, 2 by 2. They stick an ion chamber at 10 cm depth and measure what the output factor is. It's a fairly simple test. 65% of clinics, if there are 400 people here, that means probably 250 of you will go home and if you do this test, you'll find your MLC output factors, the most basic function of your planning system, are off by more than 2.5%. Means any IMRT plan you do will not, it's going to be hard to match better than 2.5%. 10% of clinics, 40 or 50 people in here, your MLC output factors do not match within 5%. We can have a great looking beam model in water, but if we don't check MLC output factors, if we don't check the things that we use to actually treat our patients, we may not be seeing the answers we want. And check back the previous slides. If you say, I don't have that, why don't I have that? It's because we haven't followed those beam modeling tips. So, quality is a team effort. Dosimetry, physics, everyone. This is a taco truck from my homeland of Houston. Great example of how everyone can pitch in, and even if the physicist isn't around to check the beam model, Carlos can still come and roll you a taco. Treatment planning tips. Now, you guys get tons of treatment planning tips. I can't really help you a whole lot with treatment planning, but I can tell you how to make a safe treatment plan. As I've said over and over, do not overmodulate beams. There are options in Pinnacle and Eclipse that control how much beam modulation that plan has. Use the lowest amount of modulation possible. Why? Because the more modulation you have, the more you magnify errors in your calculation, the more you magnify errors in your delivery. And so we need to treat with as simple of a plan as we possibly can. How do we tell how much modulation there is? Look at the number of MU. If you are delivering 200 centigrade and it's taking you 1,000 MU to get there, you are modulating your beam enormously. And you better hope that your planning system has been commissioned perfectly and that your Linac is delivering that plan perfectly. Otherwise, that pretty picture on your screen is not actually going to get to your patient. Don't have beams go through mobile parts of patients, such as arms. We actually see this a decent amount. And be aware of patient position accuracy. If they're not locked down in a vacuum bag, don't pretend that you're going to have 1 millimeter setup error or 1 millimeter setup accuracy and 1 millimeter delivery accuracy. Basically, don't create future problems for yourself, such as leaving out your laxatives and chocolate. Your chocolate laxatives, the best combination. So, after we have a plan that we have modulated as less as possible, we can look at the plan quality. We need to make sure, of course, the biggest thing is DVH objectives. Even if this patient's not on protocol, we can use RTOG and the AAPM's TG101 objectives to make sure that no organ at risk is getting too much dose. Believe it or not, we actually see this a decent amount. This analysis is available in some planning systems. We do it by default in Mobius 3D. We've actually had clinics call us up and say, wow, we normally don't check this, the lung limit, let's say, on this other type of plan because it doesn't do much lung, but it turned out we had a big case, and then just because we had lung contoured, we saw indeed we actually were not meeting the lung criteria anymore. So be very careful with DVH limits. Evaluate the target dose conformity. This is not done much in radiation oncology. I'm not quite sure why. How much dose did you pump in the target versus how much dose is outside of the patient? we look at how much dose each organ gets, but we don't always look to see, could we get better conformality? So that's something to be aware of so you can kind of get a feel for if this was a good conformal plan or if maybe this one can be improved. Now, that's a manual way of doing it. ROR, QMR, EMR reports help evaluate what was done in each structure, and they do look at things like this to make sure the plan is as good as it can be. The DVH objectives are very complex. We feel your pain. They vary by fractionation. They vary by physician. There are many types. It's not just mean dose or max dose. You get percent volume, absolute volume, volume to spare. Anyone in here that plans SBRT gets to have just a fun time with the 10 structures that all have insane types of DVH objectives, some of which, like volume to spare, you can't even really read off of a DVH chart. That's why use the tools available in your planning system. A lot of centers have created custom scripts for this. We built this in Mobius 3D, not only to check the original plan, but to check our recalculation. Stray voxels and targets. This is another fun one that people think, oh, we don't have stray voxels in our targets. When you inverse plan, IMRT or VMAT plan, it tries to throw as much dose in all target areas as possible. Every once in a while, someone along the process accidentally clicks a little pixel outside of when they're contouring outside of the target, and it turns out that's pretty hard to notice. And there's really nothing in your planning system that says, by the way, when I tried to put a lot of dose in the target, I also tried to put dose over here in this one little pixel area. I always thought there should be. There are actually, it's built in your planning system, both Eclipse and Pinnacle. You can run this check manually for your targets. We threw it in Mobius 3D. It's a simple check to do. Sometimes you can see this in your JAW settings. If you have your JAWs set to conform the target, you'll look at a couple fields and you'll say, why are these long rectangles? What's that all about? That's because there might be a little target blip out to the side. Now that we're checking this all the time, one of the things our users have been surprised about is that this lights up more than 0. Usually not a huge issue, but something to check. Always go back. Again, this is built in every TPS. Always go back for your targets. Make sure you're not telling them to put dose somewhere you don't want to be. One of the things that was recently announced that I just wanted to say I'm very happy with, McKesson, US Oncology, announced that they're going to be they have a partnership with ROR to send their dosimetrists to work with ROR to participate in the challenge plans and actually do ongoing QA for their dosimetrists. So this is a good QA tool. Everything we've talked about has been QA for equipment, QA for calculations. There are QA tools available for dosimetrists that your institution can participate in, either on a one-time basis or an ongoing basis. So pretty neat that we get to have QA on everything. Here is the QR EMR report that's done. I alluded to this earlier. It lists out all targets, all structures, and tells you when it thinks some things could be planned a little bit better. Basically, everything boils down to don't get yourself into trouble. And don't think too hard about how someone that can write, how do I land in the sky doesn't know how to land. But now that we have a great planned plan, we're going to look at dose calculation. So, general tips. We actually just had this question. Should I use the high quality setting for the final calculation? I had to explain the field of radiation oncology to my CTO when we designed Mobius 3D. It really wasn't until then that I realized how odd some things were in this field. And I explained to him that sometimes we're going to be getting dose distributions with 2mm calculations, sometimes 3mm, sometimes 4mm. Sometimes it's going to be used the CC convolution, sometimes it'll be used the adaptive convolution, so we should expect differences. And he said, well, why do you guys get to pick how accurate your patient dose calculation is? Do you pick, what was that based on? Is that based on if you like the patient? And I said, I never thought about that. It's always just been there. Why do we pick who gets the accurate calculation? And the answer is it's historical. Computers used to be much slower. We had to give people options to say, okay, no, this one we're going to have to spend 5 or 10 minutes on. That's not so much the case anymore, although with VMAT it kind of still is. And the answer to the question is we've been checking this for several thousand plans now the last few months. Sometimes it makes no difference. Most of the time it makes not much difference. Then every once in a while it makes a big difference. By big difference, 2 or 3%. That's why, one of the things he said was, we're going to perform all of our calculations at high accuracy. That's not going to be a user selectable option, how much you like the patient. The other big one we've seen, make sure the dose grid covers the entire treatment area. This is important because sometimes you'll find out that the dose grid, your planning system, isn't doing quite what you expect. If you scan a patient with their arms down, but you plan on treating them with their arms up, we've seen some people draw the dose grid around just the torso. And then in your planning system, you'll see dose just in the torso. And then you say, okay, great, well, I'll tell my patient to put their arms up, and we'll treat them like that. That's just one example of, that's not actually how that's working. Your planning system is still using the arms to attenuate the beam. If you send it over to a system like Mobius 3D, you'll see enormous failures in the arms, and you'll call us up and say, why is your system wrong? And we'll say, no, that's how your planning system's calculating dose as well. And that really leads to these last 3 things. ROI, density overrides, very, very important. Make sure, double check, all of them are correct. Make sure every CT artifact has a correct override. And at the end, always, always, always view the 3D dose that is being used for dose calculation, not the CT scan. You can do this in Pinnacle. I'm pretty sure you can do this in Eclipse as well. Say, please show me density, not the CT scan. Flip through the slices, make sure that's about what you want to treat. Make sure you don't see any huge streaks that are CT artifacts. Make sure if you overrode the arms to be 0 that they look like error. Basically, read the manual. Make sure you know what all the buttons do. This is from a microwave oven. It doesn't show up quite as well there. The chaos button. I really wish I had a good story for what that does, but it's just kind of a fun button. Dose calculation verification. So at the end of the day, how do we know that the dose we calculated for this patient was correct? I don't want to say gold standard, what we're using mostly right now is MU verification software. As Nico showed, there was the collapse cone convolution superposition, and there's the, let's say we just do our primary as homogeneous, secondary as heterogeneous, and then we'll just treat the whole patient like a water phantom. The single point MU checks are one over to the right, which is let's treat everything like a water phantom, plus let's ignore surface heterogeneities, plus let's use something that came before pencil beam, and let's just do a Clarkson calculation. That worked great 20 or 30 years ago, and as people are finding out now with IMRT and VMAT plans, that's not working great anymore. We're having to move the point around, which I'll get to later. So basically, we can't really use these for a lot of our as a QA component to check that we're delivering the right dose. We can sort of check that we're close. But we end up doing IMRT QA for any complex plans to make sure we're delivering the right dose to the patient. We recalculate. Some places can recalculate by second calculation system, second TPS. It's a little bit more time consuming. Some places, like University of Maryland, have a Monte Carlo secondary calculation system. It's a pretty neat idea. And then what we developed, Mobius 3D, is actually basically a planning system that doesn't plan and just recalculates dose using the same quality algorithm. So a lot of options available. Treatment delivery. So now that we've done the plan, we can just assume that we're going to ship that over to the Linac and everything's going to go great afterwards. Well, not according to the New York Times, it doesn't. Patient positioning is, of course, a huge one. We're not going to get into a lot. Marks on patients are great, whether or not you're using IGRT. If you're using IGRT, make sure that's QA, because that's a fun little complex system on its own. Make sure every therapist knows how to use IGRT and what all the buttons on their IGRT system do. If you get a software error, do not necessarily ignore the software error. Our field is very used to ignoring errors. This is not a good thing. And if you can, please index your localization or mobilization devices to the couch. Then you can record the actual couch values in your R&V system. Every time the patient comes back for a new fraction, you know about what the couch setting should be. It's a good way to identify large errors. Beam deliverability. You made the plan in your planning system, so it should be able to be delivered, right? As you guys have found out, not always. You can make undeliverable MLC patterns in both Eclipse and Pinnacle with forward planning. You can accidentally collide the gantry with the patient. This has actually killed a few patients as well. But these are things that we can pretty easily manually check. There are lots of tools. Probably the best way of doing it is you just mode up the field, make sure they all mode up. Some patient treatments are more susceptible than others. SPRT with couch kicks are going to be much more susceptible to gantry collisions. This is something else that we built in Mobius 3D to make sure we're checking the gantry clearance and we're checking to make sure that it's actually deliverable. There are other software, I believe, coming in the future that's going to be doing similar things as well. So a new batch of new QA tools is coming at some point soon. Linac processing. Great, so now our DICOM-RT plan has made it to the Linac. Nothing can go wrong. Well, we found out, I believe, last year that's not the case either, and I think that took a lot of us by surprise. That sometimes, either when the plan is being exported, it can crash, and sometimes the Linac doesn't interpret the sets of control points correctly. So DICOM-RT plan is really just telling the machine what to do, but it's still up to the machine to figure out how to do that. And it has complex software in there to figure out how do I best move all my parts to make that plan happen. And the machine knows it does not deliver things perfectly. So problems with exporting are back to what the New York Times says. We have an MLC plan that doesn't move for a dynamic plan. I believe that was Eclipse crashing as it exported the plan, and I believe it did throw up a warning error, but we're used to just clicking OK and not reading the error, so that wasn't caught. One real scary case was a VMAT plan was sent over correctly. Everything went correctly except the software in the Linac that figures out, is this a VMAT plan or is this a conformal arc where my leaves don't move? The leaf didn't move enough the first 5 or so degrees, and it said, oh, this must be a static arc then. And so the leaves didn't move throughout the treatment. That was a software upgrade that got fixed. So we can detect these large errors in real time by therapists, and then there's this cool thing that machines do. They actually record everything they did while they delivered a treatment in treatment logs. We can analyze those treatment logs. Again, not something that's, I think, extremely commonly done in the US. We'll talk about that in a second. So, how do we safely deliver plans? We check data transfer. I'm sure most people are used to looking at the plan, making sure that what's in the R&V system matches what was planned. We also have to be aware that what's in the R&V system doesn't always get over to the Linac correctly, since that's another transfer. We have to monitor the machine during deliveries. Your therapist should look at the plan and know, is this, what should I be expecting from this plan? Are my leaves going to be moving around? What should this look like? We can evaluate the treatment logs. But basically, we just need to stop assuming that everything went perfectly in data transfer and delivery, even though this is very frustrating because these errors don't happen that often. One of the ways we do this is IMRT QA. It can catch data transfer, machine delivery errors. It's only performed on a subset of patients, but the patients that are most likely to have these types of errors. Unfortunately, IMRT QA has a lot of sources of discrepancy. We measure something that doesn't quite match. That can be due to setup error, measurement inaccuracy, delivery error, data transfer error, calculation error, or inaccuracies because we didn't make the phantom plan perfectly. So it's a little frustrating when we get something that doesn't match. And we can't ignore bad IMRT QA results. Physicists like to do the same thing with an MU check. We send it over, we get an answer that fails, and we say, let me try that again. And then maybe it fails or maybe it passes, and we keep repeating it until it passes. We really cannot be ignoring bad IMRT QA results if that's what we're using for dose calculation accuracy as well. We have to choose solutions that actually work. Clearly, the bottle of stop chew is not doing its job very well. I don't know how many dog pictures ended up in this. So let's talk about treatment log files a little bit more. They're generated by Varian and Elekta machines. Sorry, Siemens people. I think there are treatment logs in there somewhere, but no one can access them. They include set values, which is what the Linac tried to deliver, and actual values, which is what it did deliver. They're updated 3 to 100 times a second. True beams are 100 times a second. Other machines are 3. Well, other variants are 10, and then Electors are around 3. MLC jaw positions have about 0.1 or 0.01 millimeter accuracy, and gantry collimator angles have about a 0.1 millimeter, 0.1 degree millimeters. That's a very important unit, precision. So what do we do now that we have this log file? We have to have some software to analyze it. There are a lot of places, a lot of big places, WashU, Memorial Sloan Kettering, Hospital in Vienna, a lot of others that have developed their own Dynalog analysis software. These aren't things that are commonly commercially available, but it's very important data. If you have a Varian machine, there's a free Dynalog viewer. If your IMRT QA did not come out well, throw that up in the free Dynalog viewer and see what happened. Was that because your machine didn't deliver it well, or is that because it wasn't calculated well? It works for one field at a time. Argus will actually calculate 2D fluence, works for one field at a time. I wrote fraction check. It works for thousands of fields at once, calculates 2D fluence. One of the cool things we're releasing this week in beta is Mobius FX. That's going to monitor these Linac treatment log files and recalculate dose in 3D on your patient using reference beam models, automatically calculating RTOG and TG101 limits. It's kind of hard. They're also comparing what was planned to what was set to what was delivered. They make sure the data transfer got over there, and they make sure the machine actually delivered what it was supposed to. So a lot of neat things you can do with technology in this new batch of QA tools that's being developed. How much does MLC accuracy matter? I've seen a couple papers that say MLC accuracy, 1 millimeter error doesn't matter much, and I've seen papers that say it matters a huge amount. And the answer is about the same as everything else. It depends. This is a very highly modulated plan. It's a 5 MU per centigrade SBRT prostate, 4 arcs. Unmodified, we get about a 0.5% agreement in the plan, and then when we decrease the MLC openings by 1 millimeter, you end up with about a 5.1% difference. So this shows two things. One, how sensitive it is to calculation, and also you better hope that when you deliver this plan to the patient, your leaves aren't off by 1 millimeter, which is actually a fairly common thing. VMAT treatments, we see RMS errors of somewhere around 0.6, 0.8, 1.0 millimeters. So again, you do a highly modulated plan, you're magnifying errors in calculation, you're magnifying any delivery errors you're going to have. So here's some good news. The ABR also read the New York Times, and they came up with something they called the IHE-RO QA Plan Veto Profile, a very sexy name. Basically, in a couple years, what we'll be doing is before your Linac turns the beam on, it's going to ship that DICOM-RT plan that it has in its possession off to a plan veto server. So the Linac is called a check requester. The plan veto server will be called a check provider. And the check provider's job is to detect if there are any critical errors there. Vendors, such as us, can basically implement whatever we want. Bare minimum, we're going to have to do a single point MU recalculation to make sure you don't have 3,000 MU being delivered to a whole brain, and you're definitely going to blow the patient out of the water. But once these start coming up, start looking to see what does the vendor actually do. Is it as simple as that? Do they do more? In case you guys can't tell, I love new technology. I love doing as much as possible in an automated fashion. So our solution will be basically all of this has to go right before we let you turn the beam on again in a manner that you specify. So this entire process is automatic, and again, it prevents the beam from being turned on. So even if you didn't notice the first fraction, your MLC didn't move, as long as your plan veto server did notice that, you won't repeat that on a patient. That's better than nothing. So we can at least only have one fraction of bad delivery. Tentative availability, this is taking a little bit longer than anyone would like, is maybe around 2015, 2016 for this to actually be in clinics. Online resources, my.varian.com, great documentation, QA file download, medphysfiles.com, I'll put a copy of this presentation up there. It has a lot of other good resources. rpc.mdanderson.org, RPC's website. very good website. They do talk about their common problems. They do give some reference data to look at. So, what is a modern plan check? The title of the talk. It's something that when we looking at this plan that's handed to us, as it goes down the line from dosimetrist to physicist to therapist, we recognize there are many systems at play. We recognize that the beam measurements had to be made correctly, the beam modeling had to be done correctly, dose calculation has some inaccuracy to it, patient positioning has some inaccuracy, and then the delivery is not perfect either. And we have to evaluate the plan knowing the basics of all of these components and make good decisions. And we have to QA multiple systems, the planning system, the R&V system, and finally the Linac. A lot of systems working together to get you the final answer. Now, general quality tips. This is another thing, talking to my CTO, we were kind of amazed at. And it didn't, again, you don't quite notice this until you talk to someone else. If your QA system detects a failure, does your resolution process make sense? In particular, if your secondary calculation fails, do you repeat with a little adjustment until something passes, or do you analyze why it failed? If your IMRT QA fails, do you repeat with minor adjustment, or do you analyze why it failed and figure it out? Typically, we only need, in a perfect world, we can get IMRT QA to work, and then the secondary calculation is a good backup to that. If your clinic does not have a good secondary calculation solution, and we get 10 failures in a row, and then the 11th one works, and then we pass that on to physics, and then the physicist does an IMRT QA, and that doesn't work, so we assume that must be setup inaccuracy, that must be all these other inaccuracies that don't get delivered to the patient, so we're gonna try that again. And the second time, it mostly worked, and we tried a third time, we maybe shift the patient around, make a new phantom plan. Third time it worked pretty well. What did that tell us? That there is no other field that I know of where 10 failures and then 1 pass means pass. That's unheard of. I don't know how we get away with that in delivering radiation to patients. If there was a nuclear meltdown and we found that the nuclear plant, the last time they checked their control rods, the little button that they pushed makes their control rods drop, and the logs show, well, we pushed that button 10 times and it didn't do anything, but then we hit it on the side, and then the control rods dropped, so it passed. That's not really acceptable in any other field. We need to understand when things fail, that could be saying something. It's either saying that we need to do better QA or different QA for that plan, but we need to keep doing something until we get something that we're confident passed, not just that we kept making little changes and repeating things until something passed. We need to know why it failed and why it passes now, and we need to make sure that before we deliver that to the patient, we understand that it's a good plan and that we expect it to pass. And if we can't, we can lower the modulation and it'll probably pass better. So, go back, think about your QA system, analyze if there's any parts that could be done better. Basically, over and over, if you see something's wrong, take action. Even if your action doesn't fix the problem, just labeling it, telling other people what to expect is a good first step. It's a lot better than silently just letting things continue to spray Mountain Dew or Tropicana on other customers. So, in summary, treatment plans have enormously increased in complexity over these last 10 or 20 years. Ensuring safe treatment planning and delivery is very complicated. We have a new batch of QA tools coming out. Everyone needs to understand all the systems involved, what the QA tools can do, where to look for errors. When we see errors in our software, in our QA process, we cannot ignore them. We have to figure out why they happened and at least have an understanding and at least tell others when we see that. And finally, look, I recognize we can't actually QA every single part of every patient's delivery, every segment of every MLC field we make. We have to intelligently look through this process and figure out, we have to understand the whole process and figure out where do we have time to most look for errors and making sure the final product is delivered to the patient correctly. So, at this point, I will take any questions, and this is another good example from my childhood. We went over stop, drop, and roll. Speaking of intelligently looking for errors, I don't know if this was a common thing, but we went over stop, drop, and roll all the time in elementary school. And you just kind of assumed that people caught on fire all the time because you spent so much time learning what to do when that happens. but in reality, it's not that big of a problem. So maybe we need to teach our kids what problems to intelligently look for. Anyway, thank you very much.